Hello students, in today's class we are going to talk about acceleration time graph, which is given in chapter 1, motion in one dimension. All of you should be ready with your pencils to underline the important points in our book. The topic is given on page number 42, acceleration time graph. As I have already introduced about the graphs in the previous classes, we have covered displacement time graph, velocity time graph. Similarly, we are going to learn about acceleration time graph. We all know that graphs help us to study about slope and area under the line. This particular graph is going to help us to find out area under the line. For that, you have to underline this important point in the first paragraph. Look here, the words which are written in italics. The area enclosed between the acceleration time sketch and the time axis, we get the change in speed of the body for the given time interval. Here, you can see that acceleration time graph is going to tell about area under the line. This area under the line will help us to study the change in the speed. For different graph, we have studied area under the line gives us different quantities. For acceleration time graph, the area under the line will help us to study the change in the speed. Later in this video, I will show you how to calculate this speed. And remember this point, for this present topic, we will not talk about slope. We will be focusing on area under the line. Now look at the first case given in the book. Case 1, the body is stationary. Underline this. The body is stationary. When we say the body is stationary means the body is at rest. The body is not moving, and anything which is not moving means velocity is 0. And we know that acceleration is a quantity which depends upon rate of change in velocity. When there is 0 change, it means acceleration in the body is 0. Now, how I should represent this data in the graph? Look here. Here, this axis, which is the y-axis, is carrying acceleration. Y-axis represents acceleration. And the x-axis represents time axis. It is going to be same for rest of the graphs. Whenever we talk about y-axis, you will write down acceleration. Whenever we talk about x-axis, we will write down time axis. Now, here this O, which is the origin, it also represents the 0 value. Now, because we have acceleration 0 for all the time interval, you can see here I have shaded this region. Here I have drawn this line with the pencil, which along the x-axis. Okay, so when you are asked to draw the graph for body at rest, which graph? AT graph. For AT graph, body at rest, this will be the line which is along the x-axis. Is this point clear? Now let us see the another scenario for this. Body at constant velocity. When we say constant velocity means that velocity is not changing, speed is same. For instance, the object is moving at 50 km per hour for all the time intervals. That means constant velocity case. Now, if I want to calculate the change in velocity, that is final minus initial velocity, the value will come out to be 0. And we know acceleration depends upon change in velocity. If change in velocity is 0, acceleration will be 0. Now for this scenario, how to represent the data? The data will be this. The graph will be this one, the same graph which we have shown for body at rest. acceleration on the y-axis, time on the x-axis, but because acceleration is 0, you will show a line along the x-axis. Now if I want to show the corresponding velocity time graph for this constant velocity, this will be the constant velocity graph. Okay, so this is the velocity time graph for object at moving with constant velocity, which we have studied in our previous classes also. Now let us look at case 2. If the body is moving and the speed is increasing uniformly with the time. Now when the object is moving and the velocity is increasing, how do we represent our VT graph? Let us look here. This VT graph shows that the velocity is increasing. Yes, this slant line shows change in velocity, means object is accelerating. So when the body is in uniform motion, that is velocity is increasing uniformly, means the positive acceleration is there. Now how to represent this data as our AT graph? Again, acceleration on y-axis and time on x-axis. The line will be parallel to time axis. Okay, so this line which is above the time axis shows that it is a positive acceleration. We all know that origin, the line which is above the origin shows positive y. So this positive y means positive acceleration, and positive acceleration, if we want to represent, we have to draw a line parallel to time axis. Why parallel to time axis? Because the object is in uniform motion, or you can say that this is a graph for uniform acceleration. Uniform acceleration happens when velocity is increasing uniformly. So here I have shown you the corresponding velocity time graph for this acceleration time graph. This we have covered in our previous classes, and this graph you can relate it to the acceleration time graph. Now, as I have already told you that in acceleration time graph, area is an important quantity, area under the line. Now let me show you how we will conclude change in speed using this area under the line. Look at this graph. This is the line PQ. And if I want to calculate change in speed from this graph, I will shade this region. I have shaded this region under the line PQ. Now, after shading the region, what type of figure you are getting? I am getting a rectangle. This figure PQRO is a rectangle. And we know how to find out the area of the rectangle. Area of the rectangle can be found out using length into breadth formula. So this area under the line is equal to area of the rectangle. Area of the rectangle is further equal to length into breadth. Here my length is OR and breadth is OP. So I have substituted the value for OP. OP gives me acceleration and OR is giving me time. Acceleration into time gives me velocity. So very crucial point we can conclude from here that in a AT graph, area under the line is going to give me velocity. This shaded region under the line will give me velocity. So you might ask this question, you may be asked this question in the exam, which quantity we can conclude from area under the line in the AT graph? Yes, so this point is clear to everyone. Now come to the case 3. Now in this case, the velocity of the body is decreasing at constant rate. Underline this. Now in this case, velocity is decreasing. When velocity is decreasing, we have already learned that it is a negative acceleration case. Negative acceleration, which is also called retardation. All of you underline this first important point. Here is our case 3 when the body is in uniform motion, that is velocity is decreasing. We are taking the case of decreasing velocity. Earlier we have taken the case of increasing velocity. Velocity is decreasing means negative acceleration, which is also termed as retardation. This graph we have studied in our previous classes for negative acceleration, when the velocity is decreasing, a downward line we have drawn. Now corresponding to this VT graph, let us draw the AT graph. Now look here, it is the AT graph for this. Now this is y-axis, origin is here, y-axis above the origin shows the positive y, whereas the y-axis below the origin shows the negative. Now acceleration, which is in the negative sign, which is negative in this case, will be shown below the time axis. This is the time axis, which is the x-axis. Look here, the arrow is here, which shows the downward sign. Why downward? Because acceleration is negative. Negative part will come below the origin. So below the origin, acceleration is negative, and we have shown our negative acceleration by this PQ line. PQ line shows retardation, uniform retardation. Why uniform retardation? Because it is a straight line. So straight line here shows that the object is uniformly retarding. Why retarding? Because it is below the origin. And if I ask you how to calculate the velocity in this case, again we will use the same concept. For calculating the velocity for this particular case, we will draw area under the line. How I will draw area under the line? Just shade the line, just shade the region between PQ and time axis. Now here I am shading. Yes, so this region I have shaded. Now after shading the region, find out what type of figure you are getting. Here again I am getting a rectangle. So I will use area of rectangle for this particular figure, and formula for area is length into breadth. Using that formula, I will be able to calculate the velocity for this particular case. Okay. Now I have also shown here corresponding VT graph where velocity is decreasing, so downward graph. For the same scenario, if AT graph is asked, you can draw a line which is parallel to time axis but below the x-axis. Okay. Now let us look at the last case, that is the velocity of the body is changing at irregular manner. Irregular manner means non-uniform change is going on. Non-uniform motion is there. So when motion is non-uniform, velocity is changing irregularly, acceleration will be variable. Underline this point. Now let us look at the graph for a non-uniform velocity, or you can say non-uniform acceleration case. Non-uniform acceleration will be shown by a curved line. Any curved line you will draw, that motion shows that it is a non-uniform accelerating body. So here I have shown A, acceleration on the y-axis, T, time on the x-axis, and a curvy line. This curved line shows the object is non-uniformly accelerating. So we have covered many important points in this video. The first important point was that, let us recall the important point. The first important point, that area under the line in the AT graph is going to give us the slope. Is going to give us the change in the speed. Here we will not be calculating slope. Then we talked about the different cases. The first case, when the object at rest. This is the AT graph for object at rest. Acceleration is 0 for object at rest. So the line is along the x-axis. Even in the case when the object is moving with constant velocity, the change in velocity is 0. So acceleration is 0, and acceleration is 0 will be again represented by a line along the x-axis. Yes, in the case 2, the body was in uniform motion, velocity was increasing. So we have made a AT graph where the change in velocity is same for all the time interval. So the line was parallel to the time axis, and here we have done the calculation for the for finding speed for this object. And for finding speed, we have to find out area under the line. We have to shade the region below the line, which will tells us the velocity. In the last case, we have taken a body which is moving in the uniform motion, but the velocity is decreasing. Decreasing velocity means negative acceleration, and negative acceleration is represented by a line below the time axis. Yes. The last case, the non-uniform acceleration case, will be shown by a curved line. Yes. Thank you, students, for this lecture, and we will be doing some questions, numericals based on this in the next video.